For 4.5 billion years, the sun has been our engine of life. But researchers now say its story is at the halfway mark. Each sunrise carries us closer to a transformation where the sky won't brighten, it will ignite. When the red giant phase begins, Earth's oceans will vanish long before physical engulfment. Models now show surface habitability degrades far earlier. The sun's steady brightening will strip Earth of water and atmosphere long before the star swells to swallow its inner worlds. We'll show what new spacecraft and telescopes revealed in 2025 and what that means for our fate. To understand how our story ends, we must begin with how it started. Nearly 5 billion years ago, in a cold and silent cloud, the first sparks of our sun were born. The birth of our star. The birth of our star began inside a vast molecular cloud within the Milky Way, a drifting mass of hydrogen, helium, and dust enriched by earlier generations of stars. Those ancient suns had ended violently, scattering carbon, oxygen, silicon, and iron into space. When this debris mixed with raw gas, it set the stage for something new, a star capable of producing planets like Earth. For millions of years, the cloud hung in silence until a passing shockwave disturbed its balance. Gas and dust were compressed until gravity could seize control. Collapsing inward, the cloud gave rise to the dense knot that would become the sun. As material funneled toward the growing center, conservation of momentum caused it to spin, flattening into a rotating disk. At its heart, a dense protosun formed, veiled in a cocoon of gas. Initially, its energy barely escaped, seeping out as a faint infrared glow while the temperature of its core slowly climbed. Around this hidden seed, the swirling disk held the raw ingredients of future planets, moons, and asteroids. But all of that was secondary to one crucial outcome: the ignition of steady nuclear fusion. Fusion requires extraordinary conditions. Hydrogen nuclei, each carrying a positive charge, must be driven close enough together to overcome their natural repulsion. That required immense density and heat at the Protostar center. Over millions of years, gravity pushed harder, squeezing the core tighter until the balance could not hold. At 10 million degrees, the limit was reached. Hydrogen began merging into helium, releasing energy in the form of light and heat. This was the decisive threshold. The protosun had crossed into true stardom. With fusion underway, the newborn star entered a long period of stability, the main sequence, that would sustain it for billions of years. The radiation flowing outward swept away much of the gas that still hung nearby, clearing space for planets to form. At the same time, jets of plasma burst from the poles, drilling cavities in the surrounding cloud and marking the arrival of a star that had claimed its place. This was more than just another star lighting up. It was the foundation of a solar system anchored by its gravity and fed by its energy. Modern instruments allow astronomers to watch these processes unfolding elsewhere in the galaxy. The James Webb Space Telescope, peering into birthplaces like the Orion Nebula, has captured the details of disks wrapped around infant stars, threaded with glowing jets that carve channels through their natal clouds. In 2025, Webb revealed even deeper images. Disks at different stages of assembly, jets imaged in infrared with unprecedented sharpness, and cavities rich with evidence of planetary seeds. Taken together, they confirm that the sequence which gave rise to our sun, collapse, disk, protostar, jets, ignition, is universal. Our star's emergence was not singular, but part of a repeating pattern shaping countless systems across the Milky Way. The raw material of that birth carried a deeper heritage. Those heavier elements left by ancient supernovae were not incidental, they were essential. Without carbon and oxygen, there could be no complex chemistry. Without silicon and iron, no solid worlds to bind themselves together. In this sense, the protosun inherited more than gas. It inherited the possibility of rocky planets and ultimately the conditions for life. Every calcium atom in bones, every iron molecule in blood, is a fragment from long-dead stars recycled through the cloud that collapsed to form our own. The sun's ignition scattered these elements into orbit, binding them into worlds where life could emerge. When astronomers look into star-forming regions today, they are not just witnessing a remote phenomenon. They are watching echoes of our own beginning. Turbulent filaments still condense into knots, disks still spiral, gathering clumps into larger bodies. Jets still blast outward in an unmistakable signature of a star's first breath. In comparing Webb's revelations with models, scientists now place our sun's birth within that same framework with more certainty than ever. Its formation was neither a cosmic accident nor an isolated miracle. It was one link in a cycle where gravity and time recycle matter again and again. That cycle will continue. Just as ancient stars seeded the cloud that became our sun, one day the sun's own materials will return to the galaxy. Its atoms will move outward, mixing into new clouds, perhaps one day incorporated into other systems yet to form. Seen in this light, the sun's beginning was not only the start of our story, but part of an unbroken chain of stellar generations. Understanding the origins of the sun reveals our own inheritance. We are made of materials stitched together by forces acting long before Earth existed. Our world arose from the dust of forgotten suns, bound, heated, and set burning by gravity's persistence. The sun became more than a light in the sky. It became the condition of our survival, a beacon formed from matter scattered billions of years earlier. But the story of its creation only answers part of the mystery. Knowing how the sun was born still leaves open the question of how it continues to burn so steadily across deep time. To see how that newborn star kept shining for billions of years, we have to shift our gaze inward to its very heart. The heart of the sun. At the center of the sun lies a hidden engine, operating under conditions unlike anything we know on Earth. The steady glow that reaches us is not the product of fire, but of nuclear fusion, a process where the smallest building blocks of matter are forced together, unlocking energy that sustains both the star and the life orbiting it. In the core, temperatures rise beyond 15 million degrees Celsius. Immense pressure forces particles into densities where ordinary rules begin to bend. A spoonful of this material would outweigh entire mountains. Under such extremes, hydrogen, the lightest element in the universe, no longer behaves simply. Individual protons, which normally repel each other, are driven so near that they combine. This reaction is the origin of the sun's light and heat. The sequence that governs these reactions is called the proton-proton chain. It begins when two protons fuse to create a heavier particle, emitting energy in the form of neutrinos and radiation. More interactions follow in steps, adding particles, rearranging them, and ultimately producing helium nuclei from hydrogen. At each stage, small amounts of mass convert directly into energy. On a human scale, the odds of two protons colliding and fusing are vanishingly small. The barrier of their electric repulsion is simply too great. But the intense environment of the solar core, together with the strange permission of quantum mechanics, makes the improbable inevitable. Classical physics says protons never get close enough to stick together. Their mutual repulsion, known as the Coulomb barrier, should be insurmountable. Yet quantum physics allows what ordinary logic forbids. Instead of pushing directly through the barrier, protons sometimes tunnel through, appearing on the other side without crossing it in the conventional sense. This phenomenon, quantum tunneling, is the sun's true trick. Without it, the core would never ignite, and the solar system would be a cold collection of rocks and gas. Despite tunneling being a rare possibility for any one collision, the sun's sheer size and number of particles make success certain. Every second, hundreds of millions of tons of hydrogen convert to helium, releasing unimaginable amounts of energy. The process is not reckless. It is balanced. Only a tiny fraction of the fuel burns at any moment, allowing the sun to shine steadily for billions of years without collapsing or exploding. The balance between gravity, which pulls the star inward, and the pressure created by fusion, which pushes outward, keeps this system in equilibrium. Yet the power released in the sun's heart does not reach Earth instantly. Instead, photons born in the core endure one of the slowest journeys in the universe. Caught in a dense soup of plasma, they are absorbed and re-emitted countless times, zigzagging their way toward the surface. Their progress is so delayed that it can take on the order of 100,000 to 200,000 years, commonly estimated around 170,000 years for a single photon to exit. The sunlight streaming into your window today may have begun its life before human culture even existed. Want to know why photons take so long, yet sunlight seems to arrive almost instantly? The explanation comes in one line. While it may take hundreds of thousands of years for light to leave the sun's interior, once free, it travels the 150 million kilometers to Earth in just over 8 minutes. That contrast, the slow drift inside versus the swift leap across space, defines our experience of daylight. Neutrinos produced alongside photons during fusion follow a very different path. These particles barely interact with matter, passing unhindered through the sun and through us. Unlike photons, neutrinos escape the core immediately. Today, giant neutrino detectors beneath mountains and deep underwater measure them in real time, effectively giving us a live feed from the sun's center. They confirm the proton-proton chain is active, burning just as theory predicts. This direct confirmation is how we know the sun's heart is still alive and stable. The energy carried outward eventually manifests as sunlight, the vital stream that pours across the solar system. Plants transform it into sugar through photosynthesis, and everything that eats those plants, directly or indirectly, runs on the same energy. Human thought, movement, and life itself depend on mass converted into energy inside the sun. Through an unbroken chain, from fused hydrogen, to photon, to chloroplast, to nerve impulse, fusion in the heart of a star sustains every living system on our world. The endurance of the sun is not mystical, but the patient consequence of balance at extreme scales. Hydrostatic equilibrium, gravity pulling inward, pressure forcing outward, sets the tempo. At the level of nuclei, chance tunneling creates the conditions for burning. On the scale of a star, that improbability accumulates into certainty. For billions of years, these processes have generated enough energy to stabilize Earth's climate, drive its winds and ocean currents, and provide the foundation for life. Yet every shaft of light that touches the surface of the Earth also carries immense history. What appears as a fleeting beam through the leaves of a tree is older than humanity. It holds the record of unlikely physics made inevitable, of mass turned into energy by the core of a star we orbit. The sun's internal story is written in every ray falling across the world. But while the source of its power lies deep inside, what we see from Earth is something entirely different. The golden sphere looks smooth and steady, rising and setting with near-perfect regularity. Beneath that appearance, however, lies a restless outer layer where the deep energy finally meets the surface. To understand the contrast between inner stability and outward chaos, we need to turn now to the place where the sun first reveals itself to us, the turbulent surface. At first glance, the sun appears constant, a glowing disk that rises and sets without change. Yet its visible surface is not solid ground at all. It is a restless frontier where currents of plasma rise and sink, carrying energy outward in a cycle that never ends. What seems smooth from Earth is, in reality, a turbulent expanse as vast and shifting as an ocean of fire. If the surface is boiling, why doesn't the sun tear itself apart? The answer lies in balance. Gravity holds the star together even as convection churns its outer layers. In this zone just beneath what we can see, photons can no longer travel freely outward. The plasma's opacity traps them, forcing a switch to heat transfer by circulation. Hot matter rises upward, releases energy at the top, and then sinks again to be reheated. This endless circulation produces patterns visible, even from far away. The photosphere, the sun's outermost layer we see with telescopes, is covered with bright, irregular patches known as granules. Each granule is larger than many countries on Earth, yet endures only minutes before fading back into the depths. Bright centers mark where hot plasma pushes upward, while darker edges reveal cooler material sinking back down. Seen en masse, these short-lived features give the surface its shimmering, mottled texture, like an ocean of waves constantly breaking and reforming. Energy transformation is ceaseless in this restless arena. Photons freed by rising plasma scatter less and less as they near the surface. At last they escape entirely, streaming into open space as the daylight that reaches Earth in just over 8 minutes. Every sunbeam is the final handoff in a chain of energy that began hundreds of thousands of years earlier in the core and finished with convective motion at the star's surface. For centuries, the fine detail of this boiling face escaped our instruments. But by 2025, telescopes reached clarity unmatched in history. The Daniel K. Inouye Solar Telescope, perched on Haleakala in Hawaii, now resolves structures only a few dozen kilometers across. Instead of a uniform field of convection, it reveals a richly tangled surface full of motion. Magnetic loops rise and collapse in an instant, finer than technology had ever captured before. In 2025, Inouye even revealed ultra-fine magnetic curtains and striations threading the edges of granules, just tens of meters across. Structures that change how scientists think energy and heat escape into the layers above. These revelations matter because small-scale features govern large-scale outcomes. The fine magnetic knots act like twisted ropes, stretching, snapping, and reconnecting in ways that send energy upward. Though each is smaller than a city, together they shape how heat leaves the sun's lower layers and feeds the much hotter atmosphere above. Their behavior might explain why the corona, the sun's outermost atmosphere, reaches millions of degrees hotter than the surface beneath it. Plasma movements create the convection cells we see, but magnetism dictates much of the surface turbulence. Convective flows drag magnetic fields around, like nets caught in currents. As they twist and strain, those fields store energy until they reconnect in bursts. The result releases heat, motion, and new structures. In the highest resolution images, these magnetic threads look like woven filaments, tightening and loosening across the surface. The photosphere is anything but fixed. A granule swells, glows, and sinks in less than 10 minutes. A magnetic knot coils, ruptures, and disappears in seconds. Though the shifts are constant, distance hides them. From Earth, the unresolved sea of change blends into a steady sphere. But the reality is motion without pause, a shifting canvas rewritten minute by minute. This duality defines the sun. At one scale, it anchors calendars and civilizations with its predictability. At another, it is a cauldron of upheaval, where plasma and magnetism rewrite the surface unceasingly. To call the sun unchanging is to mistake stability for permanence. Viewed through modern lenses, its visible face is more like a planetary ocean, its currents vast, brief, and violent. The calm glow we perceive at sunrise or sunset conceals this truth. The surface radiates stability outward, while beneath that projection, thousands of hidden eruptions and rearrangements take place every heartbeat. The Inouye telescope reveals the illusion for what it is, an ever-thrashing ocean of plasma, ordered by no hand, constantly churning yet strangely balanced. And where magnetism becomes organized, the sun can unleash storms. Our next section: magnetic storms from a star. The sun's surface is only the outward mask of deeper forces working within. Hidden in the constant churn of plasma, magnetic fields are twisted, stretched, and tangled like ropes under stress. These magnetic knots are not stable. Sooner or later, they snap, reconnect, and release immense stores of energy. When that release occurs, storms erupt, a sudden reconfiguration of the sun's magnetic field that drives radiation, charged particles, and plasma outward at scales that affect not just nearby space but Earth itself. The most recognizable of these storms are solar flares. A flare is the sudden explosion of light and radiation when magnetic field lines high above the surface connect in new patterns. Energy that had been locked into twisted loops instantly floods outward as X-rays, ultraviolet light, and visible emission. The power scales dwarf anything humanity has ever created. These events are vast, catastrophic on human infrastructure scales, though the sun itself remains essentially unharmed. On Earth, the immediate concern lies in their ability to disturb the ionosphere. Strong flares can degrade GPS precision, disrupt aviation communications, and temporarily block high-frequency radio signals across entire regions. The storm's core is light, moving at the speed of causality itself, and so the warning time is minimal. But flares are only one half of the story. Another phenomenon carries more enduring weight: coronal mass ejections, or CMEs. Where a flare is light and radiation, a CME is raw matter. These eruptions involve the expulsion of billions of tons of solar plasma, hurled into space at speeds surpassing 1 million kilometers per hour. When a CME heads toward Earth, Our planet's magnetic shield becomes the front line of defense. Collisions between the incoming plasma and the geomagnetic field compress and reshape it, driving currents deep into the upper atmosphere. The visible result is spectacular. Auroras expanding far beyond the polar regions, glowing curtains of green and red light illuminating night skies. Yet behind the beauty, energy surges through magnetic lines on the ground. Electrical grids destabilize, satellites lose orientation, and in extreme cases, systems critical to modern life can collapse. Our history offers proof of this threat. In 1859, the Carrington event produced auroras as far south as the Caribbean and sparked fires in telegraph offices. At the time, the consequences were inconvenient but not existential. Society was not yet wired together on a planetary scale. The dangers now are far greater. In July 2012, a massive CME narrowly missed Earth by a matter of days. Had it struck, studies project satellite failures, widespread communication breakdowns, and power grid collapses across multiple continents. The global economy, reliant on precision timing and uninterrupted connectivity, could have been thrown into chaos. This near miss is widely regarded as one of the clearest reminders of our vulnerability to storms produced 150 million kilometers away. The mechanisms behind these storms are finally coming into sharper focus. Magnetic reconnection, the sudden snapping and rearrangement of magnetic field lines, has long been recognized as the trigger. Plasma flows on the sun's surface drag loops into contact, storing energy the way bent metal holds strain. When reconnection occurs, those loops realign in a lower energy configuration, and the excess floods into heating plasma, brightening light, and accelerating charged particles. For decades, theories outpaced observation because the details occurred at scales our instruments couldn't resolve. That has begun to change. The European Space Agency's solar orbiter carries instruments approaching within 1/3 of Earth's distance to the Sun. From that position, it provides high-resolution images of active regions, tracking the precise moment when magnetic loops snap and release their energy. Structures invisible from Earth now appear in startling detail, thin arcs of magnetism rising, twisting, and then breaking apart. The spacecraft captures not only images, but the accelerated particles and magnetic fields themselves, offering a direct record of events once hidden. Meanwhile, NASA's Parker Solar Probe is plunging through the extended atmosphere into regions where the solar wind is still taking shape. Crossing closer to the Sun than any spacecraft in history, Parker has revealed structures called switchbacks, kinks in magnetic fields that reverse direction unexpectedly. The spacecraft shows that fast and slow components of the solar wind link to specific surface features, tying the dynamics of storms to their points of origin. Parker exposes the microstructure of the solar wind as it emerges, transforming models of how mass and energy leave the Sun together. Solar Orbiter's Polar Vantage and Parker's in situ data are closing a gap in forecasting. By pinpointing how plasma leaves the Sun, scientists are tying magnetic disruptions at the surface directly to what a CME will later become. With this understanding, the timeline for practical alerts is tightening. Instead of vague predictions, forecasters may soon issue precise warnings of severe storms, hours or even days before they arrive. For operators of satellites, electrical firms, and governments, that extra notice is not an academic matter. It is a difference between switching networks into protective modes or finding them disabled without warning. The human consequences are not theoretical. Our infrastructure depends on a steady connection to space. Wide-area electrical grids can surge into failure when geomagnetic storms strike Earth's field. Banking networks depend on synchronized timing made possible by satellites. Communications for aviation and shipping rely on signals easily disrupted by ionospheric disturbance. Even the quiet weather of space has become woven into human survival. When magnetic storms break that quiet, societies learn again that technology rests directly on the stability of our star. The shift in perspective is profound. The Sun is not a static beacon, but a dynamic machine of plasma and magnetism. It is not passive, but restless. Its tangled fields storing and discharging energy in cycles we are only beginning to predict. Each glowing arc of polar light on Earth is an echo of this process, an external trace of a magnetic rearrangement that took place on the sun's surface. They remind us that beauty in the night sky is possible only because immense violence occurred far away. As observations accumulate, storms that once seemed sudden are proving to follow patterns. Instruments show distinct signatures in the hours before reconnection. Fields twist, currents accumulate, and loops darken before erupting. We are learning to interpret them, reshaping magnetic chaos into forecastable order. This is no guarantee of safety, but it shifts the odds from reaction toward preparation. Predictive science, however, reveals something deeper. Storms are not isolated explosions. They are part of larger rhythms, woven into the timing of the sun itself. The violent outbursts are tied to cycles that repeat with eerie regularity, reshaping the likelihood and strength of storms across decades. Understanding those rhythms is the essential next step, pointing to why some years are peaceful while others bring violent outbursts that threaten every system we depend upon. The sun's rhythms. The sun's activity does not unfold at random. Beneath the turbulence of flares and eruptions lies a repeating rhythm governed by changes in its magnetic field. For centuries, sunspots seemed irregular to the astronomers who tracked them. Dark regions appeared and vanished unpredictably, leaving only hints that some deeper pattern existed. It was not until the 19th century that scientists recognized a consistent cycle. The number of sunspots rises and falls over an average of 11 years. This cycle is not cosmetic. It signals a global reorganization of the sun's magnetic structure, reflected in storms, radiation levels, and the overall behavior of the star. The mechanism is rooted in the solar dynamo. The sun's plasma does not rotate evenly. At the equator, the surface turns faster than at the poles. This differential rotation drags magnetic field lines into tangled shapes that become concentrated near the surface. Sunspots mark the regions where those twisted fields suppress convection, leaving cooler and darker patches. As tension grows, reconnection events erupt as flares and coronal mass ejections. At the peak of each cycle, the entire magnetic polarity flips. North becomes south, and south becomes north. Over roughly 22 years, the full magnetic cycle, the sun resets its identity before building toward reversal again. This cycle has profound consequences for Earth. During active phases, the number of solar storms rises, creating more frequent risks for satellites, electrical systems, and communications networks. During quieter phases, fewer eruptions take place, but Earth is exposed to higher levels of galactic cosmic rays, which more easily reach the lower atmosphere when solar shielding weakens. The rhythm alternates quieter years with subtle atmospheric changes, followed by stormier years when technology becomes more vulnerable. For modern societies dependent on power grids and space infrastructure, the cycle is more than an astronomical curiosity. During strong cycles, expect more satellite disruptions, auroras at lower latitudes, and higher radiation risk for astronauts. In 2025, attention is fixed on solar cycle 25. Initially forecast to be moderate, it is now showing more activity than predicted. Sunspot counts are higher, fields appear more twisted, and spacecraft near the sun detect complex behavior that models had not anticipated. Data shows solar cycle 25 is more active than early projections, and satellites and probes indicate heightened magnetic complexity, raising space weather risk compared with quiet cycles. This does not yet rank among the strongest cycles ever recorded, but it marks a reminder that the sun resists neat prediction. Its magnetic processes yield surprises even under close watch. The Solar Orbiter mission has refined our view of this process, particularly at high latitudes where the cycle's polarity shift unfolds. In 2025, Solar Orbiter's instruments detected mixed magnetic polarities at the South Pole during solar maximum, documenting how the field was actively restructuring. Its SPICE instrument, measuring polar Doppler flows, revealed motions that help rebuild the global magnetic field after reversal. These observations show that the magnetic flip is not a sudden mystery but a gradual transition we can now monitor directly. What was once an inferred event can be charted in real time as the high-latitude fields shift. Meanwhile, NASA's Parker Solar Probe continues to deliver near-sun conditions, tying coronal structures to wind acceleration. Together with Solar Orbiter, Parker gives context for the cycle's impact, reconnection in active regions, redistribution of mass and energy, and links between surface magnetism and solar wind flows. For the first time, spacecraft track the chain of cause and effect from the cycle's shifting fields to the streams of material that fill the heliosphere. The effects ripple outward across the solar system. Cosmic ray intensities measured by probes far from Earth vary with the solar cycle. When solar activity increases, the heliospheric magnetic field pushes outward, blocking more galactic radiation. When activity falls, that shielding weakens, exposing planets and spacecraft to higher radiation levels. The balance alternates, greater protection at the cost of stronger solar storms, or fewer storms but more cosmic radiation. Each phase presents different hazards for crewed travel beyond Earth's magnetic shield, forcing mission planners to adapt to the timing of the cycle. Closer to Earth, the practical stakes are immediate. Satellite operators track heightened sunspot counts with the knowledge that strong flares or energetic particle events can cause electronics to degrade or communications to fail. Long-power transmission lines are susceptible to induced currents during geomagnetic storms, risking damage to major transformers. Even aviation routes that cross polar regions may face rerouting to avoid radiation. Exposure and radio loss. Engineers and flight controllers must now include space weather in their planning, not as a rare disruption but as a recurring feature tied to the sun's 11-year rhythm. Information gathered in 2025 emphasizes that predictions of solar activity remain probabilistic. Some reversals occur gradually, others more abruptly, and each cycle carries variations. Solar Cycle 25's stronger than expected activity is a clear demonstration that long-range forecasts still carry uncertainty. However, the ability to measure polarity reversals directly at the poles and to track field strengths with spacecraft represents a major advance. It transitions solar activity from a pattern inferred from surface spots into a process monitored deep into its structure. The solar cycle not only shapes storms coming toward us, it reshapes the heliosphere itself. For spacecraft at the edges of the system, the timing of magnetic cycles alters background radiation fields. For spacefarers near Earth, the cycles influence how often flight controllers must maneuver to avoid disruptions. For societies on the ground, the cycles decide whether lights stay on and whether networks function seamlessly. A repeating magnetic rhythm beneath the sun's surface reaches into the mundane details of modern life. Understanding this rhythm is no guarantee of safety, but it provides a crucial advantage. Instead of waiting for disruption, forecasters now define windows when the probability of storms is highest. Agencies issue alerts that allow airlines to adjust routes, grid operators to shield vulnerable infrastructure, and astronauts to postpone extravehicular activity. This does not diminish the sun's hazards, but it shifts our position from unprepared witnesses to active participants. Observation has become prevention, and prediction has become resilience. At the deepest level, the solar cycle is evidence that the sun is not static. It is a star in constant negotiation between stability and upheaval, its magnetism endlessly reconfiguring. The quiet years can lull us into complacency, but the alternating rhythm ensures that turbulence will return. The pace of its heartbeat is written into the structure of plasma itself, echoing across one cycle to the next. Even as we map the pace of these cycles, questions remain. What precise mechanisms determine the strength of each? Why do some cycles erupt with far more intensity than others? Missions like Solar Orbiter and Parker are now framing these questions with unprecedented detail, showing magnetic flips, polar motions, and wind generation as interconnected pieces of one system. Cycle by cycle, the portrait of a living star grows sharper. The sun's rhythms serve as a reminder of how deeply its internal processes shape our environment, far beyond the daylight we see. The reversals, storms, and shifts of magnetism not only orchestrate events on the visible surface, but influence the unseen flows of charged particles that stream outward continually. To understand what those flows mean for planets and for life, we must turn from the cycle itself to the constant current that carries its imprint into space. Solar wind, the invisible current. From our perspective on Earth, the sun's reach seems limited to the heat and light that sustain us. But beyond what we see, it constantly exhales a stream of matter that fills the solar system. This flow, made of charged particles traveling at hundreds of kilometers per second, is invisible yet persistent. Known as the solar wind, it is one of the most powerful but least apparent forces in our neighborhood of space. It does not simply shape the environment. It determines which worlds across the solar system can hold on to their skies, and which are stripped bare. The solar wind begins in the corona, the sun's outer atmosphere, where gas is heated to millions of degrees. At such temperatures, atoms shed their electrons and form plasma. The magnetic field lines rooted in the sun's surface create channels through which plasma escapes. The sun's gravity tries to confine it, but pressure from the superheated gas overpowers the pull. From this boundary, protons, electrons, and ions begin their flight outward in every direction, carrying with them the imprint of the sun's magnetic field. This stream does not fade or disperse with distance. It continues to spread, inflating a protective cavity around the sun and its planets that ends only at the heliopause, more than 100 times farther from the sun than Earth. For a long time, the mechanics of this release were elusive. Observations suggested broad patterns, but the fine detail was missing. Recent missions have begun filling those gaps. In late 2024 and 2025, NASA's Parker Solar Probe completed passes as close as 3.8 million miles from the surface, capturing unprecedented WISPR images showing the fine structure of the near-Sun solar wind. Parker tied the origins of fast and slow solar wind streams to specific surface features, revealing where these flows begin and how they accelerate. What was once theoretical is now recorded in actual measurements. The solar wind's impact is starkest when viewed across the planets. Mars provides the clearest demonstration. With early rivers, lakes, and possible oceans, Mars once had an atmosphere thick enough to trap warmth. But as the planet cooled and its magnetic dynamo collapsed, its shield against the sun vanished. Mars lost most of its atmosphere after its magnetic field disappeared. Spacecraft data shows solar wind gradually stripped molecules into space, particle by particle, until little remained. What could have been a habitable world is now barren and dry. Venus offers a different outcome. Without a magnetic field of its own, it also lies exposed to the solar wind. Instead of losing its air, interactions at high altitude altered its composition. Chemical changes in the ionosphere contributed to the runaway buildup of carbon dioxide that created today's extreme greenhouse climate. Between Mars and Venus, the examples diverge. The solar wind either erodes atmospheres away or reshapes them into suffocating shells, depending on a planet's defenses and chemistry. Against this backdrop, Earth presents a rare safeguard. Our planet's core sustains a global magnetic field strong enough to resist direct erosion. Charged particles approaching Earth are forced to arc around it, compressed on the side facing the sun and stretched into a long tail behind. This bubble is called the magnetosphere, and without it, Earth's air and oceans might not have survived. The shield is not flawless, however. Some particles sneak through at high latitudes, spiraling down along magnetic field lines. There, they collide with atoms in the upper atmosphere and excite them into light, producing auroras. Curtains of green and red drifting above the poles may appear gentle, but each flicker represents a direct trace of solar wind particles finally reaching our world. Until Parker's Solar Probe and the European Space Agency's Solar Orbiter, scientists lacked precision in understanding how solar wind becomes structured. From afar, it seemed like a steady stream. Parker showed that instead it is turbulent, shifting, and full of sudden reversals. Small magnetic kinks called switchbacks were imaged and measured directly. These sudden bends accelerate particles into new directions, producing sharp gradients in both speed and density. Solar Orbiter, observing at higher latitudes, added a global perspective, showing how fields and plasma actually rearrange as they expand outward. Together, these spacecraft reveal why forecasting has been so difficult. The solar wind is not a singular stream, but a patchwork of fast and slow flows, shocks, and waves, all shifting as the magnetic field reorganizes itself. This understanding also clarifies why space weather on Earth varies. A solar flare or coronal mass ejection embeds itself into the solar wind, traveling toward our planet on top of the existing flow. If the embedded fields happen to be aligned against Earth's own magnetic field, their impact is multiplied. Disturbances cascade into the ionosphere and ground-level infrastructures. When the alignment is more neutral, the same storm may dissipate with far less effect. Predicting which outcome will occur requires tracking not just eruptions at the sun, but the structure of the solar wind already in motion. The contrast between Mars, Venus, and Earth reveals what is truly at stake. One planet lost its potential habitability, another is trapped in a hostile atmosphere, and Earth occupies a narrow window where magnetic shielding allows life to persist. The determinant has been the invisible current acting quietly for billions of years. Spacecraft data confirms that the relentless pressure of this wind has rewritten planetary environments over time. It continues to do so, even now. This current runs without pause. It shapes auroras that drift in our skies, carries disturbances that can collapse power grids, determines radiation hazards in spaceflight, and gradually sculpts planetary atmospheres. It is both subtle and decisive, the difference between a planet with oceans and one with none. And while Earth's magnetic shield has preserved our environment, protection does not guarantee permanence. As Parker and Solar Orbiter refine the origin of solar wind flows, they also sharpen our view of long-term patterns. We can now connect changes during solar cycles to the structures that emerge near the Sun. These missions give humanity tools to anticipate storms in detail, but they also leave us facing the larger question: what happens on longer timescales when the Sun itself begins to change? What happens when the output of the star increases steadily, raising the amount of heat and radiation Earth receives? The reality is that even under protection, no environment is static. The solar wind continues its work in the Sun's own. Brightness slowly grows with time. This combination sets limits for every planet it touches, including our own. How long those limits hold is a calculation that scientists now pursue with urgency, reshaping our understanding of Earth's future. What happens when the Sun's output continues to rise? That's the subject of the next section, a countdown for Earth. How long can Earth remain a world of oceans, rivers, and breathable skies? The answer is not measured in distant billions of years, but in the steady brightening of the Sun, a change subtle over human history yet decisive across geological time. The star at the center of our system does not burn at a constant output. As fusion slowly converts hydrogen into helium, the Sun's core contracts and heats, driving a gradual increase in luminosity. That rising brilliance sets a countdown for surface habitability, narrowing how long complex life can endure. For each billion years that pass, the Sun brightens by roughly 10%. On paper, that change seems modest. But Earth's climate rests on balances so delicate that even small increases in solar input alter atmospheric cycles, rainfall, cloud cover, and temperature. The oceans in particular act as a global buffer. They absorb heat, circulate it, and stabilize the planet's climate system. Once sunlight grows too intense, evaporation begins to outpace this balance. Rising water vapor amplifies warming further because it is itself a greenhouse gas. At that point, feedbacks accelerate, locking Earth on a path toward loss of habitability. Older studies once suggested that oceans might endure for nearly 2 billion years longer, giving Earth a long, safe span before the Sun's rising output became catastrophic. But recent work has reshaped that picture. In 2025, new planetary climate simulations incorporating updated models of atmospheric chemistry and stellar evolution revealed a shorter future. According to these studies, Earth's oxygenated atmosphere, the foundation of complex life, may collapse within about 1 to 1.1 billion years. Once photosynthesis can no longer operate effectively under increased solar intensity, oxygen levels decline and surface ecosystems unravel. This prediction means the clock for advanced life is closer to 1 billion years, not 2, cutting the habitability window roughly in half. The mechanism is not mysterious. As sunlight intensifies, Earth's carbon cycle changes. Enhanced silicate weathering on warming continents pulls more carbon dioxide out of the atmosphere. While this may initially delay warming, it eventually undermines plant life that requires CO2 for photosynthesis. As plant populations collapse, oxygen production drops. Without replenishment, atmospheric oxygen begins to vanish. The process cascades. Less photosynthesis means less oxygen, which in turn destabilizes complex ecosystems. What follows is deoxygenation, a transformation that strips away the biosphere in its present form long before the last ocean evaporates entirely. The later stages are harsher still. With oxygen collapsed and oceans shrinking into vapor, ultraviolet light high in the atmosphere splits water molecules. Hydrogen drifts into space and is lost forever. Earth moves irreversibly from a water-bearing planet to one with dry continents under an oppressive atmosphere. By then, surface life would be gone, with only extremophiles or underground microbes holding on. What was once a blue and green world becomes scorched and barren, its habitability crushed by the same star that once made it thrive. These are geologic timescales unimaginably longer than anything that concerns human lifetimes. The models do not warn of collapse within centuries or even millions of years. They describe physics playing out across billions, reshaping the long-term fate of worlds. For us, this is context rather than danger. Our species and its civilizations operate inside a fleeting span that ends long before the billion-year clock runs out. But reframing Earth's future across these timescales changes how scientists think about planetary environments in general. The lesson reaches beyond Earth toward the search for life elsewhere. Astronomers often look for oxygen as a biosignature, assuming that if a planet shows oxygen in its atmosphere, it harbors flourishing biology. But the updated models imply that oxygen-rich phases may be temporary in a planet's history. The fact that Earth's oxygen could vanish within a billion years means a world glimpsed with oxygen today might already be deep into its own countdown. That tighter window changes how astronomers judge whether an exoplanet's oxygen signature today implies a long-lived biosphere or a short-lived state. The same slow brightening of stars like our Sun could mean that many otherwise promising planets pass through habitable phases more quickly than expected. On Earth, the countdown is marked by the oceans. As long as liquid water cycles between evaporation, clouds, and rain, climate regulates itself. Once that buffer disappears, runaway trajectories follow. Unlike the distant destruction of the red giant stage, the decline of oxygen and water defines a nearer boundary 1 billion years away. It does not touch humanity, yet it sets a terminal point for the biosphere. Our planet, so often considered uniquely stable, is not immune to the gradual physics driving its star. Rethinking Earth's future in these terms recasts our perspective. Complex life is not inevitable forever, but something bound by narrow conditions. Stability is not permanent. Climate, air, and oceans will not continue indefinitely. The same processes that made Earth livable ensure that habitability has a fixed span. What remains striking is how close we stand to the midpoint of that span. Eventually, the countdown reaches a second stage. Long after oxygen collapses and oceans vanish, the Sun itself will leave behind the quiet consistency of the main sequence. Its fuel supply will run low, and the balance preserved for billions of years will give way. What follows is no longer a gradual brightening, but a dramatic transformation, one that reshapes the star itself rather than its planets. Understanding when Earth ceases to support life is one part of the story. The other is what happens when the star at the center of this drama crosses its own threshold, shifting from quiet stability to extreme expansion. That transformation marks the true end of the familiar Sun and sets the stage for the next chapter of its evolution. The red giant awakens. The Sun's long equilibrium cannot persist forever. As hydrogen fuel in the core is gradually consumed, the balance that has defined its steady light begins to shift. Roughly 5 to 5.4 billion years from now, the central supply of hydrogen will be so depleted that fusion in the core ceases. Gravity overwhelms the exhausted center, forcing it to contract and heat. Fusion continues only in a shell of hydrogen surrounding the core, while the outer layers respond by swelling outward on an immense scale. The star starts its transformation into a red giant, marking the onset of its final luminous stage. As the inert, helium-rich core contracts to densities far beyond current conditions, temperatures climb past 100 million degrees. This ignites helium fusion, helium nuclei colliding and merging into heavier products like carbon and oxygen. The ignition is not a gentle process. In stars of the Sun's size, it comes as a helium flash, an abrupt surge of released energy buried deep inside. Though veiled from outside view, the effect triggers vast restructuring in the star. The Sun's visible surface expands and cools, its color shifting toward red, but its total output jumps to thousands of times its present brightness. To outside observers, the star's identity as a stable, yellow main sequence star would be unrecognizable. Mercury will be destroyed early in this phase, its orbit too close to resist the extending solar atmosphere. Heated, vaporized, and drawn into the envelope, the innermost planet vanishes without trace. Venus follows. At 108 million kilometers from the Sun, its orbit lies far inside the red giant's swollen reach. Like Mercury, it is engulfed and erased into the turbulent gases. These losses are certain. The greater uncertainty is reserved for the third planet, Earth. For decades, scientists debated the line between survival and destruction. Some argued that Earth might escape engulfment as the Sun sheds mass, slightly loosening its gravitational grip and allowing the orbit to expand outward. Others pointed to tidal drag and the resistive pull of the expanding stellar atmosphere as factors likely to pull Earth inward. The question lingered, would our world dodge the star's body only to perish in a scorched orbit, or would it be physically consumed? By 2025, improved models have shed light while maintaining caution. Updated simulations now integrate effects that earlier ones omitted: the viscosity of the expanding envelope, friction between Earth and the star's ionized gases, and angular momentum exchange during the red giant's outflow. These refinements show that Earth's survival is uncertain and likely marginal. Many scenarios end with engulfment or orbital decay into the outer atmosphere, while a minority allow a narrow escape where Earth remains outside the swollen body. But even in those rare cases, it would be no more than a lifeless rock. By the red giant stage, all oceans and air would already be stripped away, and surface rocks would melt beneath heat far exceeding lava's glow. If Earth is engulfed, the process occurs not in a single moment, but over tens of millions of years. Drag from the giant's atmosphere slowly shrinks the orbit, bleeding energy with each passage until the final spiral begins. Drawn down through layers of stellar plasma, the planet would fracture, vaporize, and merge into the Sun's outer atmosphere. From the perspective of the star, it would be nothing more than a trace of added elements dispersed and carried outward again in the solar wind. If Earth escapes physical engulfment, it remains only as a barren, molten sphere circling at the inner edge of the dying star's influence, uninhabitable, its history erased in heat and radiation. The Sun's maximum expansion will reach well beyond Earth's present orbital distance, perhaps as far as 200 million kilometers outward. Its surface temperature will cool compared with today, producing the reddish glow characteristic of giants, yet its sheer size ensures a staggering increase in luminosity. At those scales, survival margins are razor-thin, and small variations in mass loss rates or atmospheric density can decide whether Earth remains in orbit or disappears into stellar gases. What is consistent across models, however, is that conditions required for habitability are long gone before geometry becomes decisive. While the inner planets meet destruction or destabilization, the outer planets persist at greater distance. Mars stands a chance of physical survival, orbiting far enough to remain beyond the stellar body. Even so, it would be seared and its surface altered beyond recognition. The gas giants would not be destroyed, but the radiation they experience could disturb their atmospheres profoundly. Moons of Jupiter and Saturn, worlds encased in ice today, might briefly thaw under the flood of new light, creating alien environments lasting only a short astronomical moment. These changes, dramatic as they are, pale against what happens closer in, where Earth once lay. The story of the red giant phase is less about timing precision than about inevitability. In this stage, the calm main sequence Sun gives way to instability and wave after wave of expansion and loss. Every planet within the inner system becomes vulnerable, and the delicate world that sustained biology for billions of years does not survive in any recognizable form. Models diverge on the exact sequence of engulfment, but they converge on a larger point: for surface life, for oceans, and for breathable skies, the end comes far earlier than the star's final collapse. Whether Earth is ultimately swallowed by the star or remains nearby as a charred, lifeless core, the distinction matters only on a technical chart. The outcome for life is identical. Worlds within the inner system lose their stability, their surfaces remade, their histories erased. When the Sun undergoes its swelling transformation, the time of habitable oceans and air is already long past. The red giant marks the beginning of the Sun's departure from the form we know. The expansion reshapes planetary orbits, erases inner worlds, and turns a stable star into an unstable spectacle. For Earth, its fate lies at the narrow edge between near certain destruction and uninhabitable survival. But either way, the surface life that once thrived here cannot endure. Whether Earth is swallowed or cooked first, the result is the same: extinction long before the sun's final fade. Next comes an even stranger chapter, when the star's immense outer layers detach and light the void with their last appearance. The final light show. What happens when a star reaches the end of its fuel and its stability unravels? For a star like the Sun, the finale is not a sudden implosion but a drawn-out release. Nuclear burning in the core stutters and then fails, gravity forces the center inward, and pressure surges into the star's remaining outer layers. Loosened from their anchor, those layers begin drifting outward in surges of gas and dust. The result is one of astronomy's most striking phenomena: the planetary nebula, an expanding envelope that carries the last visible mark of the star across space. The name Planetary Nebula is a historical artifact. Early astronomers peering through small telescopes thought the glowing disks resembled planets, though in reality they had nothing to do with them. These threaded, luminous clouds are not worlds but the outer parts of dying stars. Radiation from the stripped-down core makes the lost material glow, lighting faint arcs and knots that stretch for light years. Each band is formed in stages, mass lost in uneven pulses over thousands of years, accumulating as layered structures. Their shapes may be spherical, lopsided, or stretched into wings and lobes. Some appear as concentric shells, others unfold in chaotic knots, influenced by companion stars or magnetic fields. At the center sits the star's exposed core, contracting inward under its own weight. As it shrinks, its temperature rises dramatically, becoming hot enough to shine with intense ultraviolet light. That radiation energizes the gas nearby, causing hydrogen, helium, oxygen, and carbon to blaze in distinct hues. The nebula turns into a luminous chart of what the star once made, each glowing color corresponding to an element forged during nuclear fusion. The view is both fragile and instructive. These displays exist for only tens of thousands of years, brief compared to a star's multi-billion-year life, before fading as the gas thins and disperses into the surrounding galaxy. Modern instruments are revealing these finales in striking detail. The James Webb Space Telescope, with its infrared sensitivity, has captured structures never before resolved. It records filaments as thin as threads, arcs layering one over another, and waves of dust embellished with emission lines of oxygen and carbon. Webb's spectra confirm that the gas is expelled in pulses, not all at once, and trace the chemical composition carried away. Such images anchor theoretical models to direct evidence, transforming planetary nebulae from mysterious clouds into laboratories for studying how stars relinquish their mass. The Sun will one day add its own nebula to this gallery. Compared with the grandest examples formed by heavier stars, it will be modest in size and brightness, but still luminous enough to be seen across interstellar distances. As its discarded atmosphere glows around an exposed white core, the view to distant observers would be a faint ring, or bubble, a halo glowing for a short astronomical moment. For tens of thousands of years, this spectacle will remain, drifting farther until the gas is too diffuse to see. At that point, the nebula dissolves into empty space, its brief light having faded from the galactic scene. Although shaped as endings, planetary nebulae play a role of renewal. The expelled shells are rich with oxygen, carbon, nitrogen, and dust grains containing metals. Mixed into the broader interstellar medium, these materials seed the molecular clouds that later collapse into young stars and their planets. A nebula is therefore both conclusion and contribution, an end for one star that becomes the beginning for something else. Matter forged in stellar cores does not vanish. Instead, it changes form and re-enters the cycle that builds new systems. When the Sun casts off its shell, it will enrich space around it, delivering elements that could someday form into worlds orbiting stars yet unborn. The nebulae we see through telescopes are, in that sense, previews of our own star's future. The Helix Nebula, with its delicate eye-like rings, shows what expanding gases look like when seen from close proximity. The cat's eye reveals lobes and arcs piled upon each other, testimony to repeated bursts of ejection. The Ring Nebula, with its sharp circle of glowing gas, offers one of the simpler examples. Each of these observed structures stands as a visual metaphor. This is what the Sun will become. And because their gas remains ionized for only tens of thousands of years, they remind us how fleeting the final phase appears on a cosmic clock. For the distant life forms or civilizations that may still exist when our Sun reaches this stage, The view will not be one of abrupt silence, but of slow unraveling. Over millennia, the faint expanding light would drift outward, a halo against the galaxy's background. To them, the nebula would seem a spectacle of soft brilliance, a living star turned sculptor of delicate arcs in space. But to us, anticipating, from the vantage point of today, it will be only imagination, an attempt to picture the end of our star's visible life. In that end lies a kind of symmetry. A star that once condensed from dust and radiation will disperse its matter back into dust and radiation. Its final visible act is not collapse into darkness, but emission, color traces marking its chemistry, echoes of the processes that made planets and enabled life. Those glowing shells will be the sun's final visible gift to the galaxy, a brief, beautiful whisper that the elements will survive. When the gas finally disperses, only one question remains: what is left behind at the center? For at that moment, the nebula fades, but a dense stellar remnant continues, holding nearly half the mass of the Sun in a sphere no larger than Earth. It is here, in this compact survivor, that the story of the Sun's final transformation continues. The white dwarf remnant. When the glowing shell of gas disperses and the nebula fades, what remains is the Sun's condensed heart. Stripped of its layers and with fusion extinct, the stellar remnant stabilizes as one of the strangest objects in astrophysics, a white dwarf. The Sun will end as a carbon-oxygen white dwarf, a relic compacted into a sphere about the size of Earth while holding around half its original mass. What once illuminated the solar system is compressed into a dense ember, thousands of kilometers across, yet still exerting the gravity to hold planets in orbit. Its density is extraordinary. A teaspoon of such matter would weigh tons, an everyday measure pressed into extremes beyond imagination. This density is not sustained by fusion, but by an altogether different force. Gravity attempts to crush the core further, but it meets resistance from quantum mechanics. Electrons, forbidden by physical law from occupying identical states, produce a stabilizing effect known as electron degeneracy pressure. It is this pressure, not nuclear fusion, that halts collapse. The result is an object no longer growing or burning, but persisting because the structure of matter itself resists being packed tighter. The delicate balance that once relied on fusion shifts permanently to quantum law. At its birth, the white dwarf glows with residual heat. Its surface temperature may exceed 100,000 degrees Celsius, radiating light not because reactions continue, but because energy remains stored in its compressed body. With no fusion to replenish that energy, gradual cooling takes over. The visible heat diminishes as it radiates away, leaving the dwarf dimmer with each passing billion years. This slow fading continues until the object becomes too cold to shine in any detectable spectrum, a theoretical stage called a black dwarf. None yet exist because the universe at 13.8 billion years is far too young for white dwarfs to have vanished into complete darkness. The timescales of this cooling extend well beyond familiar comprehension. White dwarfs lose their energy over many billions to trillions of years. Even long after new stars stop forming, when galaxies quiet into slow decline, white dwarfs will still linger, faint and cold reminders of stellar generations that lived and died before. They are not only the embers of stars, but also markers that stretch across cosmic time, existing into eras future astronomers cannot inhabit. For our solar system, the birth of a white dwarf means a profound rearrangement. As the Sun ejects its mass in earlier stages, its gravitational pull weakens. Planets and minor bodies will drift into wider orbits, circling the dead remnant at greater distances. Mercury and Venus will already be gone, Earth reduced to rubble or engulfed, but the outer planets may persist, revolving in silence. Moons, asteroids, and dwarf planets will continue their motion, bearing witness to what remains at the center. Not a yellow star blazing in balance, but a dim fragment of its former self. Despite the starkness, the transformation is far from without legacy. The elements produced during the Sun's active life do not remain trapped in the white dwarf. They fill the gas already expelled, enriching the interstellar medium with carbon, oxygen, and other atoms forged in stellar reactions across billions of years. These materials carry outward, seeding the conditions for new stars and planets. Though the dwarf itself will eventually fade, the matter forged under the Sun's pressure continues to migrate through the galaxy, ready to be folded into structures not yet formed. Astronomers see in white dwarfs more than remnants. They see clocks written into the universe. The cooling of these objects follows predictable patterns. By measuring temperatures and luminosities of white dwarfs in clusters, scientists can estimate how long individual dwarfs have been fading, and thus constrain the ages of the clusters themselves. White dwarfs allow researchers to reconstruct stellar histories long after the original stars are gone. Then, entire chapters of galactic evolution can be traced, all from the slow fading of cores now billions of years old. For the Sun, this clock will tick across epochs beyond any relevance to human history. Still, its future as a white dwarf situates our star in the same continuum as countless others already cataloged. What seems like a personal, singular end is revealed as a common thread in stellar evolution. The result is extraordinary density and unimaginable timescales, but also a form so predictable that it helps measure the lifespan of galaxies themselves. To imagine the Sun's conclusion in this way is to see its existence as part of a greater cycle. Its brightness will diminish, its surface will cool, and ultimately it will blend into the background of stars long dead. Yet the atoms built inside it, from the calcium in bones to the iron in rocks, will not disappear. They will drift outward with the expelled atmosphere scattered through interstellar space. In this way, the white dwarf does not signal only absence. It marks transition from active star to enduring matter, written into everything that comes afterward. For humanity and for life, such stages are far beyond reach. Our story will close long before the Sun's white dwarf forms. Yet by studying stars that already occupy this phase, we see what awaits. The process is neither dramatic collapse nor violent implosion, but a slow surrender to physics. A shrunken star hollowed of fusion, shining faintly until heat itself depletes, persisting as one of the most stable remnants in the universe. Although its light will fade, the Sun's elements will keep on working, passed outward to future generations of stars and planets. The end of its visible fire is not a clean ending, but part of a continuum where even the quietest remains contribute to renewal elsewhere, linking death with the prospect of new beginnings. The legacy of dying stars. When the luminous gas of a nebula disperses and only the ember of a white dwarf remains, the legacy of dying stars begins to reveal itself more clearly. The final act of stellar life does not erase a star's history, but distributes its achievements across the galaxy. The Sun, like countless stars before it, will end by giving away what it has created: carbon, oxygen, nitrogen, and the other essential building blocks that its nuclear furnace forged across billions of years. These elements disperse into space where new stars and planets can one day form. The death of a star is not disappearance, it is redistribution. Astronomers now trace this cycle directly. The interstellar medium is far more chemically rich than it would be if only the Big Bang's primordial hydrogen and helium remained. Supernovae, stellar winds, and planetary nebulae have all seeded the void with heavier elements. Without this process of enrichment, rocky worlds like Earth would be impossible. Silicon, iron, phosphorus, and oxygen, materials at the heart of oceans, mountains, and biology, were all released during the deaths of earlier stars. The continuity of life itself depends on this cycle. Today, instruments confirm how these endings work. The James Webb Space Telescope has captured remarkable detail within fading planetary nebulae, recording emission lines that trace carbon, oxygen, and sulfur as they stream outward, and even showing structures that resemble the first ingredients of dust grains. Beyond individual eruptions, Webb has imaged massive star-forming regions such as Sagittarius C, revealing protoplanetary disks where those redistributed elements accumulate. These disks already show carbon-rich molecules and indications of water, offering a direct link from stellar death to the conditions that support habitability. Evidence also comes from systems that endure after a star's final collapse. White dwarfs sometimes reveal heavy elements in their atmospheres that should not be present. Under normal conditions, they would sink too quickly to be observed. Their detection implies rocky debris from destroyed worlds is constantly raining down. Around some dwarfs, entire disks of wreckage circle in place, remnants of planets and asteroids ground apart by gravity and collisions. Other white dwarfs even show worlds still intact in orbit, survivors of the parent star's violent expansion. Together, these observations prove that stellar death does not have the simplicity of erasure. Instead, matter rearranges, reforms, and sometimes begins new cycles of evolution under the gravitational pull of these stellar remnants. Supernovae extend this principle further by creating the heaviest ingredients in the periodic table. Elements like gold, uranium, and iodine cannot form during normal fusion processes inside stars. They require the brief, violent extremes of collapse and explosion. Though the Sun will never take this path, its contribution continues the same narrative. Stars finish their lives by sharing matter, and galaxies transform that matter into new systems across repeated generations. The physical composition of our own bones, blood, and atmosphere records this truth. Each atom of calcium or iron entered the solar nebula because other stars lived and died before the Sun existed. The Sun, too, will pass forward its matter. Earth itself may not survive as a planet, but its minerals and carbon, and the chemistry born of life, will be released into space as the expanding envelope sweeps away. Cooling dust grains will mingle with oxygen and carbon expelled by the Sun, becoming part of interstellar material that collapses into new stars and, potentially, new planets. The destruction of one world can therefore enable the beginning of others, framed not as an ultimate loss but as an enduring contribution. These cycles reshape how astronomers think about habitability in the cosmos. Planets form within disks already rich in chemistry made by earlier generations of stars. This is why astronomers find organic molecules and water signatures within the birthplaces of exoplanets. But these discoveries must also be placed in the context of planetary lifespans. Recent research indicates that oxygen-rich atmospheres like Earth's might not remain stable for more than about 1 billion years under the brightening output of their parent stars. That means the presence of oxygen around distant exoplanets, a signature often treated as a decisive sign of life, may in fact represent only a temporary stage. Stellar deaths remind us that habitability is not permanent. It depends on cycles that last for limited spans before ending. In this way, both telescopic observations and planetary survival confirm the legacy of dying stars: to seed, to recycle, to invest in what comes next. Stellar demise builds the chemical stage for biology, determines how planetary systems change, and establishes the limits of life's duration. The continuity from one generation of stars to the next underscores that endings in astronomy are rarely final. They are transitions disguised as conclusions. Webb's sharp eye makes this especially vivid. Its images of planetary nebulae display gas expelled in orderly shells and clocks of chemistry unraveling against the dark. In star-forming regions, it reveals the cycle fully realized: enriched matter already collapsing into newborn suns surrounded by disks where rocky worlds are likely to appear. And among the oldest surviving remnants, Webb and other instruments prove that planetary debris continues to orbit, fall, and reshape long after fusion ends. These insights tie observation directly to theory, expanding the narrative of stellar death into a universal cycle of material inheritance. For us, this offers a perspective both humbling and profound. The Sun's ending will erase our planet, but in doing so, it will contribute to the ongoing renewal of the Milky Way. Biological life here is temporary, but the matter that once hosted it is permanent in another form. Our sense of destruction comes from a narrow focus on one world, whereas the galaxy's larger rhythm shows death consistently giving way to creation. Understanding this cycle also reveals a broader truth about our place in the universe. Life is not possible without stellar deaths. It requires repeated enrichment before complexity can arise. Without these processes, galaxies would remain sterile, bearing clouds of hydrogen and helium. Instead, billions of anonymous stars have already lived and vanished, ensuring that the building blocks of water, DNA, and atmosphere exist here. Our Sun, by ending, will one day participate in that chain. The conclusion is stark yet hopeful: death in the cosmos is preparation. Our star will not be remembered for the moment its light vanishes, but for the elements it shares in the act of disappearing. Its long history has been one of balance and stability, but its strongest legacy will arrive at its conclusion, when the products of fusion are sent outward for others to inherit. Our star's death is not an annihilation, but an investment in future worlds. And in recognizing that this cycle is measurable, visible, and already underway around countless stars across the Milky Way, we begin to see our own destiny more clearly, as part of a pattern written into the life and death of every sun. The sun's end is not speculation. It is a defined stage of stellar evolution, charted through models and confirmed by observation. What once seemed like destruction is better understood as transformation, where light and matter persist beyond the death of one star. In short, new spacecraft and telescopes in 2025, Parker, Solar Orbiter, Daniel K. Inouye, and Webb have sharpened our picture, showing both the sun's present complexity and shortening some long-term habitability estimates. Knowing our star's fate gives perspective and a reason to keep looking up. If this surprised you, like and subscribe. We'll keep tracking what these missions reveal.